to the first of our tutorials for Specialist Maths. Today's topic is a recap of one of the topics you covered in Year 11 Methods, which is the equations of circles and graphing circles on the Cartesian plane. The basic information you need from this is obviously your work with surds and fractions. It's going to come into play a lot here. And the whole equation stems from Pythagoras' theorem. So you've done a lot of work on Pythagoras' theorem over the years, and last year further developed that with the unit circle, and also methods touched on these equations as well. So our basic equation comes from Pythagoras. We're going to have x squared plus y squared equals the hypotenuse squared, or in this case it would be the radius squared of our particular circle. Without any translations, this circle will have its centre at the origin, so 0, 0, labelled point 0, point O, and any point as we revolve around the outside could be labelled P, and its coordinates would be x, y. So if its coordinates are x, y, you're going to see it's x from the y-axis and it's y from the x-axis. And those key points make up the position around the circle, and we've seen that again last year. So in general, we're going to talk about two of the possible transformations we looked at last year in methods, and you'll look at it again in Unit 3-4 methods. We're going to look at translations both vertically and horizontally, and these you're reasonably familiar with are caused by x minus h. And in this case, a little bit different. We're quite used to putting plus c on the end to have some sort of vertical translation, but here we have y minus k, which is going to be a shift of k units up and down the axes. So our new equation will be x minus h squared plus y minus k squared equals to the radius squared. And that'll be defined by a translation of xy, so any point, which will include the centre, will be moved by h units to the right and by k units up. So if you're thinking about our positive convention, h units to the right and k units to the right. So every point will move. Basically we'll create a new circle, the same shape circle, with a new centre, coordinates of h and k, and we'll see that example in a second. Same radius. I'll get you to pause now and think about one of the key questions here in terms of why we're going to look at these two transformations. So transformations, remember, consist of translations, dilations and reflections. And I'll be asking you in class next time we see this work why we only consider those two particular transformations. So getting down to the nitty-gritty and actually being able to produce some work from this. Predominantly we're going to see an expanded form, and we're going to need to factorise this and put it into, get it ready to put it into the circle form. So here you're seeing a jumble of x squared and y squared terms. So look for those in the equations. It's a good hint that this is the part of the course you're in, be it circles or what we're going to touch on in the next couple of lessons with x squared and y squared in a single equation. We've also got some other x terms, some y terms and a constant. Now they may be on the left-hand side or the right-hand side of the equation, but we are going to have to group them together. So essentially you can see the mechanics here. I've colour-coded it for you. Grouping my x terms together, x squared minus 2x, my y squared and my minus 4y are grouped together, and I've just moved the 1 across the other side. It's getting it ready for this form here. We're going to have the radius on the right-hand side of the equation. So that's what I'm doing in the first step there. The next step is to complete the square, and you've seen this all the way back when you first used completing the square to work out the turning point of a parabola. We're going to take half the middle term, so half the 2, x minus 1 squared, and then adjust that by taking away that minus 1 squared. Now it's always going to be a subtraction there, so we don't have to worry too much about the sign there, but just to see more formally, you're going to put that in a bracket, square it, take it away. Similarly with the y term, half the middle term, y minus 2 squared, and take away that remainder, that minus 2 squared. So you can see here these two will be numerical values, and they're going to contribute to the constant or the radius on the other side of the equation. So grouping it together, you could use a couple more steps here if you wished with your number work, but x minus 1 squared will be that x term, x minus 2 squared will be that single y term now, and all our numerical values head over to the right hand side of the equation to equal 4. So you've now got this equation in the form x plus or minus some value, y plus or minus some value, equals the radius squared. So you can see from this particular example here, you've got a new centre. Your centre has been translated to the point 1, 2, and you need to take the square root of that value. Only the positive square root, we can't have a negative radius, so we're going to have a radius of 2. So this circle has been moved to 1, 2, and its radius is still fixed. You're going to need to put some key points in. Obviously the inset points are going to be key points, but get a really good idea of the scale of your drawing. Put your centre in, reasonably accurate plot here, and then think about the radius. Think about how far you are away from both axes. So if this is the point 1, 2, and you've got a radius of 2, you're looking at going 2 in each direction. So 2 to the right, 2 to the left, and 2 up and down. And that'll give you an idea of the size of your circle. You can then see where your intercepts, if you are in fact going to have intercepts, would be. So here we're obviously going to cross the y-axis twice, so we'll have 2 y-intercepts. Here it looks like we're just going to touch the x-intercept, the x-axis, and we'll confirm that algebraically in a minute. And that's going to be the size of our circle. So I'll leave it as an activity for you guys to do, and I'll check this when we get into class. Actually finding those intercepts algebraically, and the technique's no different to any other graph you've met over the years. Finding x-intercepts, let y equal 0. Doesn't matter which of these forms you put it back into. You may have a preference for one of these later forms, but any of these forms here are the same equation. So you can put it back into those to find the appropriate intercept. Y-intercept, vice versa, let x equal to 0. So work through that. You should probably include that in your notes. And the solution points you should get are that point 1, 0. And you'll have points here that I've labelled down here. 0, root 3 plus 2. You're going to have a lot of work with surds in here. And 0 minus root 3 plus 2. Just check the size of those values. Root 3 is 1 point something, that's all you really need to know here, so you're looking at still a positive value. If you come up with something too big and you've crossed the axes, that's your cross-checking, and you realise you've got some sort of error happening there. So a nice way to cross-check. Lots of different examples we can do, and we'll work through a few over the next couple of lessons. But one of the things that may be a little bit new at this stage is regions or inequalities. And what we're looking at here is 2 particular inequalities. So our circle x squared plus y squared has to be less than 9, and we're also looking at some sort of linear inequation where y has to be less than or equal to x. Both now reasonably familiar graphs, but maybe not so with the regions or with the inequalities. So just plotting them as equations. With most inequalities, just think about it as an equation to actually get key points and to get the shape of the curve or the line. And then think about what it means to have an inequality, which side of the line you're going to be on. Okay, so our circle is x squared plus y squared equals to 9. Now we're going to draw it as a dotted line because we're just going to have less than values. Okay, so the indication here, the note dashed lines do not include the values. If you have a solid line, like our linear equation, you'd have a filled in line. Very similar to what you've been doing with endpoints, open circle if we're not including, closed circle if we are going to include. And that extends obviously to these regions here. Y equals to x is our linear equation, familiar one, 45 degrees, pi on 4 radians. And if we extend this to y is greater than x, then we want the y value to be larger than the x value. And that occurs on the upper side of this line. So anywhere on this side of the line, we're going to have y is greater than x. And for our circle, we want the values to be less than 9. So we're going inside the circle. So anything inside the circle will be less than 9 in terms of the circle. Anything outside the circle, okay, which is an infinite plane, we're going to have greater than 9 for that particular value. So where those 2 regions cross is both the circle, which is still dotted, and the line there. So the hashed in green region, and I've got a little key down there, that's going to be the region required to meet both of those inequalities. Okay, so the note there about the dashed line. There's some key points here again. We've got some intersection points and some intercepts as well. So to complete the graph, I'll ask you as part of your notes to go ahead and find those 4 points. And we'll talk about this key value here. The technique is obviously to solve equations simultaneously. So equation 1, make it into an equation rather than an equation. Equation 2, substitution, find those points. But there are other techniques, and I'll ask you to think about where this value comes from. Perhaps it's relation to unit circle work, key trigonometry values that we've met over the years, and that'll kick off some of our discussion in class next time. Okay, so that's all for circle work. Next time I see will be for ellipses.